Have you ever stopped to wonder how we tackle those absolutely massive problems? Like modeling global climate change or analyzing images from a telescope in deep space. Problems so big, a single computer would literally take centuries to solve. Well, today, we're going to dive into a really clever, systematic way to design programs that can handle all that by working in parallel. Let's jump right in.
I mean, this is the fundamental question, right? It's what drives the entire field of high-performance computing. When you've pushed a single machine to its absolute limit and it just can't go any faster, what do? You've got to change the whole strategy. The answer, it turns out, isn't about building a faster worker. It's about building a much, much smarter team. Okay, imagine you're trying to build a skyscraper. A single-core processor? That's like one very dedicated but very lonely worker trying to do it all by themselves, laying every single brick one by one. I mean, talk about a bottleneck. So what's the solution? You bring in a whole crew, right? Multiple cores, all working on different floors at the exact same time. And that, right there, is the whole idea behind parallel processing.
So here's what we've got on top. We're going to start with a real-world puzzle, then we'll see what happens when we try a simple way to break it down. After that, I'll introduce you to a super powerful 4-step solution called PCAM, and we'll wrap up by giving you the blueprint so you can use it yourself. All right, let's make this real. Our puzzle for today is something you've probably seen a million times, processing a huge high-def image. We want to apply some kind of cool effect, like a blur or maybe an edge detection filter. And the key is we need to do it fast, like really fast. So the specific technique we're talking about is called image convolution. And all it really means is that to figure out the new color of any single pixel, you have to look at the pixels right next to it, its immediate neighbors. So if you're doing a blur, you might average all their colors together. For edge detection, you'd look for big, sharp differences. Now, this is the key part, this dependency. The fact that every pixel needs data from its neighbors, that is the big challenge that's going to shape everything we do from here on out. Okay, so let's try and solve this thing. The first idea that probably pops into your head is, well, just divide up the work, right? Seems obvious. But as you're about to see, that simple, intuitive idea has a massive hidden catch. So this first official step is called partitioning. The idea is to take the big problem and just smash it into the smallest possible tasks. Since our problem is all about the image data, our strategy is called Domain Decomposition. And that's a fancy way of saying we're literally just going to chop up the data, in this case, the image itself. The logic seems pretty straightforward, doesn't it? The image is made of pixels. We have to calculate a new value for every single pixel. So let's just make each pixel its own little task. For a standard HD image, we're talking about millions of tiny individual tasks. I mean, what could possibly go wrong? Yeah, this. This is what goes wrong. Remember that little detail about each pixel needing data from its 8 neighbors? Well, when you make every pixel its own task, you create an absolute explosion of communication. For just a standard HD image, that's more than 16 million data connections crisscrossing between all these tiny tasks. It is a total logistical nightmare. And this really hammers home a fundamental law of parallel programming. See, all that time your processors are spending just talking to each other, that's time they aren't actually doing any work. This is what we call communication overhead, and it is the absolute enemy of efficiency. It doesn't just slow you down, it wastes a ton of energy. So yeah, our first attempt? A spectacular failure.
But hey, don't worry. That communication nightmare is actually perfect because it shows us exactly why we need a smarter way to do this. And this is where our hero, the PCAM method, enters the story. It's designed to take exactly this kind of chaos and turn it into crystal clear clarity. The absolute key to this whole thing is a step called agglomeration. Now, I know it's a fancy word, but the idea behind it is simple and incredibly powerful. Instead of millions of tiny little pixel tasks, we're going to group them together into bigger chunks. So why does this work so well? Because now all the communication that happens inside one of these chunks, it happens locally on the same processor, and that is lightning fast. It's not clogging up the network trying to talk to other processors anymore. So this is the before picture, right? A tangled, inefficient mess. You've got millions of individual pixel tasks all screaming to talk to their neighbors at the same time, creating this insane storm of network traffic that would bring even a supercomputer to its knees. And here's the after. It's beautiful, isn't it? By grouping the pixels into these big vertical columns, we've totally transformed the communication pattern. Just look at that. The only communication we need now is just between the edges of the columns that are right next to each other. We literally went from millions of chaotic connections down to, well, just a handful. It's clean, it's manageable, and it is so much more efficient. Okay, so the last piece of this puzzle is called mapping, and it's exactly what it sounds like. Now that we have these nice, big, manageable tasks, or columns, we just have to assign each one to an actual processor that's going to do the number crunching.
Now, when we're doing this mapping, we have two main goals. First is load balancing. You want to make sure every processor gets a roughly equal slice of the pie, so you don't have one processor finished early and just sitting around idle while another one is still swamped with work. And second, you want to minimize communication. So if two of our task groups, like two columns next to each other, need to talk, you put them on processors that are physically close so that conversation happens as fast as humanly possible. All right, so we've totally cracked our image processing puzzle, but now it's time to zoom out. Let's take what we just learned from this one specific example and turn it into a reusable blueprint, a framework that you can apply to just about any parallel design problem you can think of. Remember way back at the beginning, that first step, partitioning? What we did is called domain decomposition. We split up the data. In our case, the image. Each worker got a different part of the image. But it's really important to know there's another way to do this, called functional decomposition. Think of this one like a factory assembly line. Instead of splitting up the thing you're working on, you split up the jobs. Each worker, or processor, becomes a specialist at one specific step in the process. So it's really about this. Do you split the data, or do you split the work? And here it is, the whole shebang, the complete PCAM method. It's a super clear 4-step blueprint. First, you partition. Break the problem into the smallest possible tasks. Then you analyze the communication, figure out how those tasks need to talk to each other. Next, you agglomerate, group those tiny tasks into bigger, more efficient chunks to cut down on that communication overhead. And finally, you map those new, bigger tasks onto your actual processors. PCAM: partition, communication, agglomeration, and mapping. That's the framework. So if there's one thing you take away from all this, it's this. You have to think about communication costs right from the very beginning. Don't just chop up a problem and hope for the best. You have to analyze how those little pieces are going to need to interact. PCAM gives you a systematic way to do that. And honestly, that agglomeration step, that's usually where the real magic happens. It's the key to turning a tangled, inefficient mess into a lightning-fast solution. And all of this leaves us with one last pretty big question to think about. We live in an age where the amount of data in the world is just exploding, and the challenges we're trying to solve are getting bigger and more complex every single day. So will this kind of parallel thinking, the skill of breaking down huge problems and managing all their messy interactions, stop being a niche skill just for computer scientists and become a fundamental way that all of us need to learn how to think?